So I think two or three subtopics are left. What I would suggest is leave some space for it. It is completely independent topic. So yeah, I'll start ray optics. Ray optics and optical instruments. So later remind me, okay, like how I did with that eddy currents. I'll teach on one Wednesday or something. So now we'll start with a fresh topic, that is ray optics and optical instruments, right? So first, we need to understand the term optics. So what do we mean by the term optics? Hello? So what does optics mean, guys? Optics means a branch of physics, write it down. So branch of physics which deals with light. So if I'm able to talk about the branch of physics which deals with light, you call that branch as optics. Okay. So under optics, the classification takes part as two types. One is called geometric optics, which is also given a name called as ray optics, and the other is called as physical optics, which is given a name called as wave optics. So if you observe, right, in this chapter, we will be mostly concerned about ray optics. Are you able to understand what I'm trying to say? Right. The next question is, why are we calling geometric and why are we calling it as physical? Because there are 2 points. Whenever you're trying to classify something, right, you need a differentiating factor. So if you observe the differentiating factor, that is dependent on size of the object and wavelength of light. Okay. So here when I say light, right, what light am I trying to talk about? I'm trying to talk about visible light. So in the previous chapter, if you revisit the electromagnetic spectrum, what is the wavelength associated with the visible light? It is somewhere between 400 nanometer to 700 nanometer or 4000 angstrom to 7000 angstrom. This is how it works. So when you say nanometer, it is 10 power minus 9, which is a very, 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 very small value. And angstrom is obviously again a small value. Right? Now comes an important question. If the size of the object with which the light is interacting, for example, we have devices around us, and because of light is what you're able to see something. If I switch off the TV and ask you to, or I make the brightness of this TV to 0 and ask you to see, you will not be able to see. Or there is no intensity coming out. So light is interacting with different objects in the sense, for example, the tube light is there. Those who are online, you will be able to see a reflection here in the screen. Yes, sir. Right. So this tube light is giving out some light which is interacting with the walls. And it is because of the reflection, you're able to see the color of the walls, you're able to see the color of the table and everything, right? So if the size of the object with which the light is interacting is very large, I repeat it. If the size of the object with which the light is interacting is very large compared to the wavelength of light, then light is treated as a ray. So write it down. If the size of the object, with which light is interacting, the size of the object with which light is interacting is very large compared to the wavelength of light, light is treated as a ray. On the other hand, if the size of the object, is comparable to the wavelength of light, the size of the object is comparable to the wavelength of light, the light is treated as a wave. Okay. Light is treated as a wave. Those who are online are able to understand? Yes, sir. Clear?
Yes, sir.
Yes, sir.
So listen to this very carefully. In your lower grade, that is your 10th standard, you would have learned this ray optics, right? Under the name light, reflection and refraction. Right? So when I talk about light, it basically exhibits certain phenomena. What do I mean by phenomenon here? Phenomenon means something which can be seen with our eyes, something which makes us believe because we are able to see it. So reflection is something you can see. So where all do we see reflection in our real life? For example, you are able to see this color because of the reflection. You see yourself in the mirror because of reflection. You are able to see in this because of reflection. The level of intensity keeps changing. That's a different thing. But there is a phenomenon called as reflection. Then what about the other phenomenon? It's called refraction. So whether you treat light as a ray or as a wave, it still exhibits the phenomenon of reflection and refraction. It does. Okay, however you do, it will show. But if you recollect the concepts that you have learned, light, reflection, and refraction, if you recollect the objects with which the light was interacting, what were the objects? They were either mirrors or lens. Right? So now try to connect the dots and see the definition that I gave you. Where light is interacting with objects whose size is large compared to the wavelength of light. In the sense, when you talk about a mirror, you will not take a mirror whose size is nanometer and try to look at your face. Maybe of this size or something which is in terms of at least few centimeter, if not maybe in terms of meter, at least in terms of few centimeter. So when you compare the centimeter with angstrom, obviously it's a high value. That is why we treat the concepts, we try to understand the concept behind these kinds of mirror, whether it is a plane mirror or a spherical mirror, with the help of ray optics, because it is easy for us to analyze. Right? So now that you can ask me a question, can I not do it with wave optics? You can very well do it, but the problem is You'll have to go with a lot of mathematical equations which involve trigonometry. Because what happened in alternating currents? Something was changing with respect to time. Electromagnetic waves, we wrote an equation y is equal to a sin kx minus omega t. Okay. The size of the objects are bigger, right? So whether you talk about a lens or a mirror. I was saying that if you have to treat the concept of reflection and refraction of the depth of waves, you need to be very good with math. And too much of math gets involved. So to simplify that only, they started treating it as a ray. So based on that concept, let's start discussing the different phenomena that is exhibited by light. Okay. So let's see what it is. Thing is, first, when I talk about the first phenomenon of light, it exhibits the property of reflection. So reflection is not deleted. Okay, last year it was deleted. This year it is there. So concentrate. So what is reflection is? So bouncing back of light when it strikes a smooth and shiny surface, right? Are they able to understand this point? So when I talk about reflection, what kind of objects exhibit reflection? Mirrors, basically. So mirrors exhibit the property of reflection. So for you to experience reflection, how should that particular reflecting surface be? One side it is supposed to be transparent and the other side it is supposed to be opaque, right? So if I have a boundary where one of the sides it is transparent and the other side it is going to be opaque, then this surface exhibits the phenomenon of reflection. Am I clear with this? Right. So when you talk about reflection, there are two important rays that we discuss about. One is this transparent, this is opaque. So you have something called as an incident ray, and you have the bounced back ray, which we call it as reflected ray. So if I take this to be I, and if I take this to be R, right? So if I take it like this, then there are two laws associated with this, which is called as laws of reflection. What are they? Incident ray and that's right, and normal lie in the second angle of incidence is equal to angle of reflection. So what do I mean by angle of incidence here? Angle is measured between two lines. Angle between the incident ray and normal. What do you mean by normal? Normal is a line which is drawn perpendicular to whom? To the reflecting surface. To the reflecting surface. Is that clear? Incident ray, reflected ray, and the normal all lie in the same plane. Okay.
Sir, can you scroll up for a second? Sir, a little more. The definition part.
So why I use the word smooth and shiny surface is because in reflection itself there are two kinds. One is called as regular reflection and the second is called as irregular reflection. So regular reflection means only in the case of regular reflection if its angle of incidence is equal to angle of reflection. That is why I was very particular that the surface needs to be smooth and shiny. In the case of irregular, what will happen? It will get randomly bounced back. Is it clear? Shall I proceed?
Yes, sir.
So angle of incidence is equal to angle of reflection. Okay. So what do you mean by this point? Incident ray, reflected ray, and the normal all lie in the same plane lengths? What do I mean by the same thing? Never visualized it. Say this is the reflecting boundary. Okay. If this is the incident ray, listen to this. If this is the incident ray, then the reflected ray should be in the same plane. It's not like incident ray will come like this and reflected ray will go like this. Because if the incident ray is coming in this way, you have drawn a plane through it. So incident ray is like this means reflected ray should also be in the same plane. So if you are a incident ray should not go like this, or it should not come out of the XY plane. That is the meaning. Okay. Next. Reflection by a plane mirror. So if I take a plane mirror like this, one side is transparent and the other side is opaque, obviously. So if I have, let's say, a surface like this, okay, this is the surface on top of which this plane mirror is placed. Okay, I'll make it even more realistic. Let's say this is the surface on which it is placed. Okay, this is the surface on which it is placed. Side level button. Screenshot. So if I take this as AB, okay. So let's say you're standing in front of it. Now what can happen is you can have two reflected rays, right? You can think of two reflected rays based on which you can locate the position of image. So how should I take the two reflected rays? If I take one, instead of taking parallel, can I say perpendicular to the reflecting surface? So if I take a ray perpendicular to the reflecting surface, what is the angle of incidence here? It is 0 degrees. Most common mistake made is they take it as 90, which is wrong. So it is 0 degrees. If the angle of incidence is 0, angle of reflection is also 0. Similarly, if I take a ray to be incident like this, okay. So if I take it to be in this way, then this is the angle of incidence. Then the angle of reflection will be like this. I could have taken here also. I could have taken a real ray like this and like this also. It still makes the same thing. So angle of incidence is equal to the angle of reflection. If you observe, one of the reflected rays is in this direction and the other reflected ray is in the diverging direction. So obviously they both are not going to meet. So the only option for us to make them meet is extend them in the backward direction, as if the mirror was not existing at all. When I extend them in the backward direction, they meet at a point which we call it as the point where the image is formed. So if I look at this, this will be A dash and B dash. Is it clear? Am I clear with this? So it will be formed in such a way that if this distance is x, the image is formed at the same distance x on the other side as well. And what kind of image is formed? So it is a virtual image. And virtual images are always erect. Remember, virtual images are always erect. Real images are always inverted, virtual images are always erect. Real images are always erect. Okay. So those two distances will be the same. And with respect to a plane mirror, the image formed is laterally inverted. So you know what is the meaning of lateral inversion, right? So means left will start appearing as right and the vice versa. Is that right? Okay. So what else is there? That's it. So next we'll see how does a reflection take place through spherical mirrors. Okay. So write down the heading as spherical mirrors. So what do you mean by spherical mirror? Right. So if I have a curved surface, and from that curved surface, if I'm able to take a small portion out of it, okay, the small portion is taken in such a way that this part is selected. That is, if I break it into two parts, I get a major segment and a minor segment. So out of the minor segment, I'll take the smallest value that is possible. So when I take the smallest value that is possible, then if it is made opaque on one of the sides, right? Depending on which side you are making it opaque, whether it is the depressed side or whether it's the bulge side, depending on which side it is made opaque, the spherical mirrors are classified into two types. What are they? One is convex and the second is concave. Okay. So if I silver it on the outside part, okay, that is the bulged part, then this is called as a concave mirror. If I make it opaque on the depressed side, it becomes a convex mirror. Okay. So with respect to a spherical mirror, there are parts. So parts of spherical mirror okay. So if I take parts, then see. I'll explain it with concave and convex parallel. Okay, listen to this. If I take the center of the mirror, what do I mean by center of the mirror? Center of the, it's not the center of the sphere. Center of the curved surface. If I take the center of the curved surface, that is called as pole. Means for the curved surface, you will have exact center. No? That center of the curved surface is what we call it as pole. And here also you have something called as pole. Is that right? Okay. Similarly, if you take the center of the sphere of which the mirror is taken out, from which the mirror is taken out, then that is called as the center of curvature. So here also you have center of curvature. Is the point clear? So did you understand the difference between pole and center of the pole? Is the center of the curved surface. Center of curvature is the center of the sphere of which the mirror was a part of. So if you draw an imaginary line passing through the center of curvature and pole, you call that as the principal axis. So it is called principal axis. Okay. Now you have something called as focus. What is focus? How did you get that point? First of all, how? What light rays appear to converge or diverge? Source is at infinity. When the source is at infinity, what will happen to? When a ray is taken parallel to the principal axis, then after reflection, what will happen to it? It will pass through a point on the principal axis itself, which is called as the focus. But for you to locate the position of an image, what do you need? You need two rays. I took only one ray. But for this first ray that you have considered, how will you consider the reflected ray? So at the point of incidence, right? If you draw an imaginary line passing through the center of curvature and the point of incidence, you call that as the normal. Then this becomes I, and the ray after reflection will cut the principal axis at a particular point. Right. In a similar way, if I take a ray along the principal axis itself, then what is the angle of incidence? 0. So angle of reflection will also be 0. Okay. So those two rays meet at a point on the principal axis, which we call it as focus, or to be more specific, we call it as principal focus. Am I clear with this? Okay. Similarly, if I take a ray parallel to the principal axis for a convex surface, right, it will get diverged in this direction. Similarly, if I take another ray along the principal axis, it will pass without any deviation. So when I join these two, then this will be the focus. Breathe out. So for a concave surface, for a concave mirror, you have a real focus, whereas for a convex mirror, you have a virtual focus. And wherever virtual means, what will happen? The images formed will be erect. That is why if you see convex mirrors are the ones which are used in the rear view mirrors, in the vehicles. Because if a bus is traveling, right, you want to see that bus when you want to cut a right. Or how should the object be? It should be erect. If it is inverted, you will get confused. Is that clear? Am I clear with this point? No. This is the angle of incidence, this is the angle of reflection. So by now you should have understood how to draw the normal. Normal is an imaginary line that is joining the point of incidence and the center of curvature. Is it clear? Anything else? Any other point that is existing? So we have discussed everything, right, about this. Now, the next point is called as aperture. So what do you mean by aperture? It's not ability, it has something to do with length. Yeah. So if I take this as AB, if you draw a line from A to B directly and measure it, that length is called as the aperture. Basically, sometimes they call it as the diameter of lens or diameter of the mirror. So aperture is what? It's not exactly the length of the mirror. It is a line that is joined between the ends of the curved surface. The length of the distance between the ends of the curved surface is what we call it as aperture. Okay. So in your lab purpose, for your lab purpose, right, the kind of mirrors that we use are mirrors with less aperture. Okay, or no, I'll not say less, I'll say mirrors with a small aperture. Is it clear? So now let's think of the formula called as, before we see what is mirror formula, let's see the relation between focal. See, I'm not going in depth because I'm assuming you already learned these things. So whichever is important, I'll explain. Relation between focal length and radius of curvature. Okay. So first of all, what is focal length? The distance between the pole and the focus. What is radius of curvature? Distance between the pole and the center of curvature. So whatever I'm going to derive here is applicable for both concave and convex. Okay. So for derivation part, I'll carry with a concave. If you see, for me to define the focus, I need to take the object at infinity. So if I take the object at infinity, a ray is parallel to the principal axis. A ray after reflection will pass through a point on the focus. Yeah. So if I take a ray parallel to the principal axis, after reflection will pass through the focus, and you have the center of curvature here. Through the center of curvature and a point of incidence, right? I'm drawing a ray which is called as the normal, obviously. Is that right? So if I take this angle to be theta, how much is this angle? It is also theta, right? Because angle of incidence is equal to angle of reflection, right? So if this is theta, how much is this value? Why? Alternate interior. Yeah, there theta. It is so what will happen? What will be this angle? Which will be 2 theta. Yes, this will be theta. Right. This will be theta because alternate interior angle, and this will be 2 theta because exterior angle is equal to sum of opposite interior angles. Is the point clear? Now, when you're doing this derivation, the first thing that you need to have in your mind is aperture is small. When the aperture is small, then you can say that the curvature is small. Are you able to understand what I'm trying to say? When the aperture is small, you can say that the curvature is also small. What is the curvature? If I take this as A, if they take this as P, AP is looking like a curve, right? Right? AP is looking like a curve, no? But actually what will happen is, this is a zoomed version of the mirror that I've taken. The point A is actually close to the principal axis. So remember, if there is a ray, listen to this carefully. If there is a ray closer to the principal axis, you call that as paraxial rays. If a ray is closer to the principal axis, you call it as paraxial rays. And the ray is far away from the principal axis, you call it as marginal ray. Is that point clear? Right? Am I clear, guys? Those who are online are able to understand?
Yes, sir.
Okay. So aperture is small and the curvature is also small means that the angles involved are also there. Angles involved are also small. When angles involved are small, then sine theta can be approximated to theta can be approximated to tan theta. Now, what we can do is, when I say the curvature is small, then I can say AP is like this, and this angle is theta, and this point will be C, where the distance between PC is called radius of curvature, and the distance between AP is AP only. Similarly, if I look at the triangle APF, APF, okay, this angle will be 2 theta. So AP and AP are common in these two. So from the first triangle, what is tan 2 theta? AP by R. But here there is something called as sign convention that we need to follow. So when I talk about sign convention, generally the point P is taken to be the origin. And if you divide it as the basic coordinate system, anything measured on the left is considered to be negative. Anything measured on the right is considered to be positive. So AP divided by R means R is negative, minus. R is on the tan theta, sorry. Tan theta is AP by R, minus R. Then what is tan 2 theta? Minus F. So tan theta can be approximated to theta, and tan 2 theta can be approximated to 2 theta. Is that right? So theta is equal to AP by minus R. 2 theta is equal to AP by minus F. So 2 into, in the place of theta, I can write AP by minus R is equal to AP divided by minus F. AP and AP are gone, which implies F is equal to R by 2. The focal length is equal to half of the radius of curvature. Under what scenario? When will you be able to derive this kind of a situation? Only when the aperture is small and the rays you have considered are paraxial in nature. This is point clear. So focal length is equal to half of the radius of curvature. So the last concept that is left out in this topic is mirror formula. I'll just give you the outline. Okay, now like I'll explain it peacefully. I'm getting continuous calls. Okay. So tomorrow we'll have early 6 to 7 because nobody is there. Can come up. Director. So tomorrow and day after also we can have from 6 to 7. Okay. So if I take this to be the pole, this to be the focus. So before I explain the mirror formula, I have to explain you the ray diagrams. So Ripatik, I'll draw the diagram. So let's say you have considered an extended object that is placed beyond the center of curvature. So when you take a ray parallel to the principal axis, after reflection, will pass through the focus. When infinity means ray is parallel, no? It is like this ray is coming from infinity only. So when I consider a ray parallel to the principal axis, after reflection will pass through the focus. And when a ray is incident at the pole, then the principal axis itself will act like a normal in such a way that this angle, if I take it as I, then the angle of reflection will also be in such a way that this angle is also taken to be I. Is that clear? So both will intersect in such a way that the image is formed between the center of curvature and the pole, where it is a real image. Why did I say real image? Because with respect to a mirror, if the object and image are on the same side, it's real image. And another important point I told you, real images are always inverted. Observe. Okay. So I'll just give you the outline. So the distance between B and P is called as object distance. And the distance between B dash and P is called as the image distance. And the distance between the focal length, focus point and the pole is called as focal length. And mirror formula is 1 by V plus 1 by U is 1 by F. Okay. So basically mirror formula gives you the relation between object distance, image distance and the focal length. So one important point I would like to stress here is, whenever you are deriving a formula in this chapter, you need to use sign convention. And whenever you are applying the same formula, you need to use sign convention. So you use sign convention twice. Why is it so? That a reason I'll explain it tomorrow. But remind me about this question. Why we are doing it. Is it clear? So I repeat, sign convention is applied during derivation and application as well. Clear? So this is a diagram, and with this diagram, we'll continue our next lecture, that is tomorrow, where I will derive. So I have to go out actually. So yeah, another calls. That's it. So in your 10th grade, you would have applied this formula. You would have applied sign convention, but you would have not known why the formula. So how the formula is actually come. So formula derive we need to use sign convention. I'll explain tomorrow what will happen if you don't use it. So yeah. Those are all clear.
Yes, sir.
Yes, sir.
We'll wind up this. So tomorrow's class is at 6 o'clock. Tomorrow and Wednesday both.
Okay, sir.
Yeah, okay, sir.